So I wanted to get you started for your second exam problem from Chapter 7, and it deals with computing shear and bending moment diagrams. So all that this is a visual representation of how the shear force and bending moment change as you move along a beam. So one thing you might notice is there is no normal force diagram, and that's because beams traditionally are intended to be loaded perpendicular to their span, and under that assumption, you will never have any internal normal force. So even though you're determining shear and bending moments at any point along the beam, the problem setup for this works the same. The first thing you want to do is analyze your entire beam in equilibrium. So notice that this beam has a pin connection at A, but since there is no horizontal force, that pin connection will only have a vertical reaction associated with it. There's a pin connection at Y as well. And we notice that this uniform density load we can model as a single force applied directly at the middle of the beam. Again, because this is a rectangular density, the centroid of that shape is right at the middle, and the intensity of the force is just going to be the integral of this curve, which for a rectangle will just be W times 2A. So I'll write 2AW. So what do you notice about this beam? If I sum all moments about point B, you'll notice that the vertical reaction at A would tend to induce a clockwise rotation, but there's nothing to counterbalance that. So what that's going to show you, if you do the math, is that under this loading condition, you actually don't need the reaction at A. And we know this, we've known this since we were kids, and you try to balance something that's uniform. You know if something has a uniform mass, you can balance it by placing a single finger underneath the center of mass. So if this is a uniform force, then a single reaction placed directly underneath the centroid of this uniform force would serve to balance it. And that's what it's showing you. You don't need AY. And if I sum Fy, what I find, of course, is that the reaction at B is just the entire intensity or the magnitude of the equivalent of that distributed load. So in order to do a shear and bending moment diagram, what you want to do is ask yourself, what portions of the beam can I make cuts, like here, 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 here? If I made a cut anywhere in there, obviously the free body diagram will change, but will it essentially be the same? Will it very simply as a function of what I'll call a distance x, where x is a distance measured from the leftmost point of the beam? So if I were to take and chunk this beam up, as long as this distance is less than A, and we can argue about the less than or equal to case. Your book doesn't really get into that, so you don't need to worry about it. Basically, what we'll do is we'll just not let either place a strong definition on the values of the shear and bending moment a day. So if it's discontinuous, we'll just let it be discontinuous. So what would this free body diagram look like? Well, as long as I'm less than A, I'm never going to pick up that reaction at B. So all that will happen is I'll have a varying portion of the distributed load. Well, the distributed load in any case, if I take a chunk x of it, is just going to have a magnitude wx. It's just going to be applied at lengths x over 2 from the left and from the right. And then what is counterbalancing that affected model of the distributed load to keep this in equilibrium? Well, it must be the internal shear force and the internal bending moment. So if I sum all forces in the y direction, what do I find? Well, I find that the equivalent magnitude of that portion of the distributed load, Wx, and that is minus, so it should be, it's in the downward direction, so by our sign convention, it's negative, minus V has to be 0. So what that means is that V must be equal to minus Wx. So that just looks like simple math, but what is it saying? It's saying that the tendency of this beam to shear is increasing as we move away from the left end. And that's kind of related to that idea that we talked about at the beginning of Chapter 7, where generally speaking, the stresses in a support structure aren't uniform across the length. And that's why the cross sections aren't uniform. You make them larger at places that need more support due to higher internal stresses. What about the bending moment? Well, if I sum all moments about point x and set that equal to 0, notice that the model of the distributed load is going to tend to induce clockwise rotation, counterclockwise rotation, so it'll be positive. What is it going to be? Well, it's going to be Wx is the magnitude of the force. What is the perpendicular distance? Just x over 2. And what other moments are acting upon this? Well, not the shear force, because it goes directly through point x, just the bending moment m. And we always assume the bending moment to be in the counterclockwise direction. That's why your book, be careful on this one. When your book says follow the sign convention, I think that was the last problem. They said follow the sign convention, but this is the sign convention, that if you're analyzing from the left to the right, the shear force goes down and the bending moment goes counterclockwise. So if that were to be equal to 0, what does that tell us? That tells us the m has to be careful with your math here, wx times x over 2 is going to be just minus w over 2 times x squared. So that would be quadratic. And that's not surprising to us because we know that as you move further and further away from the support, in terms of the rotation that's going to be induced, when you have more distance, you not only get more force, but this perpendicular distance gets longer as well. So both of those expanding as a function of x gives you this x squared. So what a bending moment diagram does, and a shear diagram, is actually plot how these vary as a function of x. So I could plot v as a function of x. Well, what would this look like? Well, this is just a linear function with a slope of minus w and no y-intercept. So this is valid all the way up until x equals a. So when x equals a, what would be the value of this? Minus wa. In a similar fashion, I could plot the value of the bending moment. So this is in newtons. This would be in Newton meters. And that will be nothing more than a quadratic function that kind of has, remember when a quadratic function has a negative slope, it just means that it's going to have this kind of concavity. So actually, let me, sorry, I do a sketch. You can actually plot, I drew it with the wrong concavity, sorry. That's what I get. I'm trying to, just like you all, I'm trying to rush this up for the semester. I can't wait to teach and actually have time to prep. This has been the craziest semester ever, but you kind of, it needs to get steeper as you go down. There you go. There you go. And you can plot in some points of it, but if you want to determine what that is, this is at the location x equals a. So if you plug in a to there, it would be minus w over 2a squared. Okay. So I'm going to leave, this is linear, and this is quadratic. So for the problem on your test, what they're basically going to ask you to do is they're going to give you this loading, and they're going to say to pick which of the shear and bending moment diagrams is correct. So what I've given you here is half of the shear and bending moment diagram. So what you want to do before you start your test is complete for x between a and 2a. And the only thing that's going to change there is you're still going to have your model of your distributed load, which still, for a variable distance x, will have magnitude of wx, right? But what you're going to need to add in is your reaction at b. And remember, your reaction at b is 2aw. And if this is some distance x, well, how far away is that reaction at b always from point A? It is always a units away. So you're going to be able to compute that this distance here, which you're going to need for your moment, is just the total distance x less a. So that's the free body diagram that you're solving in order to determine the portion, sorry about that, of the shear and bending moment diagram to the right of x equals a. So don't be surprised if you see a discontinuity in one of these two functions, particularly if it's the top function. You should find that they follow the same tendency, though. The shear moment should still be linear, and the bending moment should still be quadratic. So I hope that that was a very, very quick 9-minute introduction to what a shear and bending moment diagram looks like. The key thing to know from a practical point of view is it's useful for visualizing how these internal stresses change as you move along a beam, and it allows you to determine where to make the beam sturdier. And hopefully you see basically all these problems work the same. The only way you can change them is to just vary the loading structure on top and vary the geometry of the reactions on the bottom. So if you're really confident how to do this problem, you can pretty much ensure that, along with the previous problem we did, that you could do any problem from Chapter 7. So although we're only spending about an hour total in lecture on these, know that we covered it pretty well. And that's kind of going to be the case, as you'll see, for Chapters 8 and 9 as well. There's not a lot of new content, particularly on chapter 9. If you're comfortable with integration, that's a very, very easy chapter, kind of one you can just do a couple examples of. And I'll just kind of do it the same way that I did this lecture. One learning module to get the general point, and then one example problem. And the friction one will be a little bit longer. Maybe we'll need 3 learning modules and 2 example problems. I'm going to end up splitting the final into 2 sections just so everyone can get started. So it's Sunday night now. I have all the chapter 7 content done. So I have 2 questions from chapter 7. And then towards the end of last week, after the chapter exam 2 material, I gave you kind of 2 similar things for chapter 6. One was the analysis of those vice grips, and another was a method of sections problem. So from the new stuff for the final exam, there's 2 questions for chapter 6 that you have halfway solved. There's 2 questions for chapter 7 that you have halfway solved. I'll post that as a My Lab assignment and just basically go through those videos, make sure you know how to do all of the solution, and just get ready to enter your answers in on the assignment. And then we'll do the same thing for chapters 8, 9, and 10. As I mentioned, probably a question or 2 from 8, 1 from 9, and 1 from 10.